So let's talk about what we're going to talk about and sort of go through the rest of the what's going on. So today is Thursday. We're going to be talking about chemical equilibrium, position of equilibrium, factors that influence equilibrium, K, Q, and Le Chatelier's principle. We're going to get the pre-lab. You should have picked it up as you came in. Almost everybody last period was able to finish the pre-lab and sort of get things ready for the next time, plus work on sapling. So there's not a lot of notes left. Okay, next time we come, we're going to work on the equilibrium lab. That will be part of the period. It won't be the whole period. That's Monday. So you can finish that and probably finish the lab notebook and turn it in that day. But it's up to you. If you don't want to turn it in that day, you can work on sapling. Thursday is going to be a cleanup day. Tuesday is the ACT for just juniors, and the pre-ACT for sophomores. Both need to be here at 7:25. Seniors get the day off. Woohoo! But if you need help, we're open for help in the afternoon as teachers. So if you need some help, you can come back then. Test is open starting this Friday and only open till next Friday. Okay, so if you're off on Tuesday, that might be a good day to go take the test. Okay, kind of thing. Or if you want to get it done this weekend, you can get it done this weekend because you'll have all the information that you need. Okay? Make sure you do the pre-test. Make sure you finish your sapling before you do that. Last sapling is today. I know I had 8.5 good. I only think you have 4. Is that right on this one? I think you only have 4, so I put an extra 2, it looks like, just because I got in one of those modes. Okay, all right, so we're going to start. So if you grab out your notes, we're going to go ahead and go into equilibrium and dynamic equilibrium. This covers the Utah State Core, Standard 5, Objective 2A, and here we go. So when we look at a graph of concentration versus time, this is where we just have one thing that we're looking at. And if the reaction goes to completion and is not in equilibrium, then we will run out of bromine because the reaction will stop because we run out of bromine and we're done. But when we have an equilibrium, the reaction can go forwards and backwards. And so we come to a place where as much is going forwards as is going backwards, or the same amount is going forwards and backwards. It doesn't have to be exactly the same. So on this one, as we look at the graph, the rate at which it's decreasing at the first part between like 0 and 1 is very fast. But as we get closer to the end of the reaction or end of the play out of the reaction, it actually slows down. So as it slows down, the slope also gets more gradual because our slope is directly related to our reaction rate. Okay? As we look at a graph, and this is the kind of graph that you're going to be doing on your experiment on Monday, you will have both reactants and products on the same graph. Now, people think equilibrium is going to end up like the top graph on the left, where they equal exactly the same at the end. But that's not true. That happens very, very, very few times. It's more like the other 3 graphs, where sometimes they switch places and come almost up to where the opposite one was, and sometimes they switch places and don't come very close to each other, like the middle graph, and sometimes they don't even cross each other, like the very last graph on the right. You are going to have a reactant and a product that you're going to be putting on the graph that you do on Monday. We're going to be stressing the system after it comes to equilibrium. So after it comes to this point where it doesn't change, where the slope is 0, the rate of reaction is overall 0, then we're going to stress the system and see what happens. We're going to do that 2 times, and on the 3rd time we're going to figure out what is going back and forth. So when we talk about state of equilibrium, that is a state at which we don't have changing amounts. In other words, our rate of reaction is 0. There's still things going backwards and forwards, but there's no increase or decrease in the rate. When we get to equilibrium concentrations, that's that point at which I keep doing and I keep getting the same answer. I keep getting the same concentration. I keep doing over and over. So my line is flat. So I end up with a flat line. Any questions with these graphs? Because you're going to be making you're going to actually be making 3 different graphs in your lab on Monday, I would suggest you do them in Logger Pro because it's really fast and easy to do in Logger Pro. All you have to do is add another column and you've got the 3 columns and you just input the data and you're done. But you can use Excel if you would like to. But you're going to have to print 3 graphs. Okay? So the graphs will somewhat look like this. We're going to tweak the, say we get to this point of equilibrium, then we're going to change something so these are not going to look the same. We'll end up with another kind of thing going on after. Okay? But you're going to have 2 lines. Okay, so as we talk about an equation, here is a generic equation. And the lowercase letters represent the coefficients. The uppercase letters represent some chemical compound. So when we talk about position of equilibrium, we're talking, is it towards the reactants or towards the product that it's moving? When we talk about an equilibrium expression, we actually go products over reactants. Did you have a question or just? Okay. So we end up with this expression. Now this expression is used for a lot of different cases. In chemistry, if you go on in chemistry, there's tons and tons and tons of different Ks. This is KEQ. You use the basic same thing for all Ks. It's products to their coefficients over reactants to their coefficients. What is included? We only include aqueous. Oh, I forgot to do this first. Sometimes we don't have concentrations, so we have gases. And gases have pressure. It's the same thing. The only difference we've done is the pressure of C to the C power, the pressure of D to the D power. But it's the same setup. So you can basically use the same setup for both of them. But sometimes you'll see it used in parentheses and the P there. Don't freak out. That's why I put that side one there. It's the same stuff, okay? The P just means pressure. So if I have a gas, it's really hard to get a concentration, but it's easy to get a pressure. Okay? So we use that. What we do put in are gases and aqueous. So in the KQ expression, we use gases and aqueous, and that's it. So if there is a solid or a liquid, it drops out. We just ignore it. Pretend it's not there, because that doesn't affect the equilibrium. So the bracket that you see in the KEQ, the bracket means molarity. So anytime you see a bracket around something, it basically means what's the molarity of it. And so I'm going to take the molarity of C to the C power, so whatever the coefficient of C was. If it's a 1, great, it's a 1. If it's something else, then I'll put that there. And sometimes instead of KEQ, when it's a concentration, we say it's KC, meaning K of concentration. So there's lots of different Ks. There's Ks of solubility, there's Ks of acids, Ks of bases. But it's all set up the same way. Products over reactants to their coefficient. So let's use some of these or figure out what this means. So as we're looking at K, I thought I put the other equation I did. It just is. So we're looking at our K equation and we plug in numbers. If it equals 1, that just means I'm at equilibrium. My products are equal to my reaction concentration. If my KQ is bigger than 1, well, if you look at the equation, my products are on top and my reactants are on the bottom, so that means I have more products than reactants. If my KQ is less than 1, remember products are on top, reactants are on the bottom, that just means I have more reactants than products. And that helps us to know which way the reaction is going. So remember, on this one, it's not a one-way reaction. It's a reaction that can go forward or backwards. So if I have more products than reactants, then I know the reaction likes to go forward. If I have more reactants than products, I know that the reaction likes to go backwards. It doesn't like to go forward very much. Okay? Giving you a chance to write it down so you don't get pen cramp. I make myself move over here if you haven't noticed, so I don't keep going, because it's fast for me. Okay, so let's actually do, did you need it a little bit longer? I heard a, okay. So let's actually do this. Let's actually do a KQ with an equation. So we've got this equation up top, and it's gases. So we would use the pressure, but I'm just going to have you use the concentration thing. So KQ is equal to, we're looking at the products first. So if I did concentration, I would do CO2 to the 4th power, and my water would be H2O to the 6th power. That's my products, right? My reactants are concentration of C2H6 to the 2nd power and concentration of O2 to the 7th power. I did check and make sure that they were all gases or AQ. Now if I wanted to, or if it shows it out to me as a KP, which would be the pressure of CO2 to the 4th power, the pressure of water to the 6th power, the pressure of C2H6, which is ethane, to the 2nd power, and the pressure of oxygen, I forgot the P, of O2 to the 7th power. It could also be written that way. Yes?
I thought the equation was like you put the coefficient in front of it.
Not in front of it. The coefficient actually goes to the power. So see how the little a and the big A? The little a is the concentration, the big A is the concentration, the little a is the coefficient, which becomes the power. This is just a generic equation that I'm writing this from. Okay, so what I'd like you to do is I'd like you to do the next two, but I threw in one that you're not going to use. Which ones don't you put in the KQ? Solids or liquids? Can you see a solid or liquid that you're not going to put in? Water. So I just, when I see that, I go like that so I don't put it in the KQ, and I know it doesn't belong there. So would you go ahead and just write the KQ, and I'm okay if you write it with pressure or if you write it with concentration. You just need to know that they're basically the same. The only difference is the P, they're looking for a pressure, the brackets are looking for molarity. But it's exactly the same. Okay, don't look up until you've got the middle one done, and then you can look up and check it. I'm going to put it up. Okay, how'd you do? Thumbs up, I got it. Thumbs down, I have no clue what I'm doing. Okay, good, thumbs up. So, you missed it? Okay. All right, so the next one should be fairly easy too, right? They're all AQs. So this one I do use brackets. I'm not going to use the pressure at all. So go ahead and look down, do yours. And then if you got it done, go ahead and look up, and we'll put it up here for you. Oh, brackets, sorry. That's a 6 at the end if you didn't notice. That sort of looks like a funky, oh, yeah, now it even looks better. Okay, how do we do? Did you get it done? These should be very fast and easy to do. We okay with them? Okay, yeah, you keep the charges with them. This bottom one had the charges, so you still put the charges within the brackets. Brackets just mean concentration. All right, so let's go ahead and go on to the next page. We should be able to, and I've added another one here just as an example, so you can put it at the very top of the page if you'd like to. We should be able to look at a KQ and write a balanced equation very quickly. So on the top one here, I've got products. Remember, it's going to be a double-sided arrow like this. And I've got products being HI. It's to the 2nd power, so I put a 2. On my reactants, I would go H2 plus I2, and I've got my balanced equation. Would you do the next two? So write the equations for A and B. Remember, products are on top, reactants are on the bottom. Don't look up. I'm going to do A. Look up when you're done. Check and see if you got it right. If you got it right, go ahead and go on to B. I'm going to put B up. Don't look up unless you want to see B. Okay, B is up. How many got both A and B correct? Thumbs up. Or, yeah. Okay, anybody get one right and one wrong? Anybody got two wrong? All right, so we're getting this pretty easy, right? All right, so we're going to go forward. We're actually going to now use it where we actually have the concentrations and we've got to figure out the KEQ. So first up, I look and I find that they've given me a balanced equation right here. So I'm going to write the KEQ for that. Take a second, do it on your own, then look up and see if you got it right. Okay, the next thing that we're going to do is we're going to actually take, and they've given us the concentrations here. So we're going to plug them in. So I'm going to take 9.2 and square it. I'm going to take it and times it by 0.2. Then I'm going to divide it by 1.31 squared. So go ahead and put that through and let's see what we get. I should have asked, did everybody get the first one? Did I lose anybody on the first? Everybody okay? Yes, ma'am. You're okay? All right. I don't want to lose anybody, and I forgot to stop and ask. So grab out your calculators. There's some up here if you need to borrow mine. They're in the box right there if you need to. Okay, when somebody's brave gets the answer, let me know what it is. 9.6? 9.8. 9.8. Since we only have two, that would actually be 9.9, right? And I'm dropping my pen and making it fall apart. This is all good. 9.9. Okay, KQ does not have any units, so you do not have to put any units on it. What does this tell me about the reaction? 0.099. Do I have more reactants? Do I have more products? I have more reactants. So when I write the equation, the 2NOCl, I have more reactants, so there's more going this way and a little bit going that way. Okay, so this is telling me I have a lot more reactants than I do products. Okay, if I had a number bigger than 1, then I would have more products than reactants. Okay, let's go forward. So now we're going to look at then just the K's and sort of get an idea of how much we have compared to the other. So here we have 2.10 times 10 to the minus 6. How do the reactants and products add up? Which one do I have the more of? Which one? Reactants or products? Reactants. I have a lot more reactants than products. Not so much. Okay, so let's look at the next one, 0.15. I have more reactants, but not a lot more, right? Because this is a very, very small number. This one's not as small. So I have more, but not a lot more. And I have sum of the products. Okay, let's look at the next number. 1.2 times 10 to the 8. Which one do I have a lot of? Products. I have a lots of products. And little over here. Okay, then the last one, 0.000243. Reactants. Where does it fit between A and B? Is it between it? So I'd say somewhere. Since we got a lot more, so somewhere will go between it. So now I need to take those and I need to arrange them. Which one had the smallest amount of product? A. Okay, so A had the smallest. Then what came next? A. Was it B? B. Okay, then D, and then what? B, and then C. Okay, so you need to be able to look at numbers and be able to arrange them according. They might say more reactants next time to less reactants, or they might say less reactants to more reactants. But you need to be able to rearrange it. Just remember always, it's products divided by reactants. So then I can say, okay, if it's a small number, I have more reactants. If it's a large number, I've got more products. Okay, so that gets in your head. Okay, so then we're going on to Le Chatelier. Le Chatelier's project, or principle, basically is like a teeter-totter. If I add a stress to the system's going to react to relieve the stress. Okay, so if I'm standing here and I've got equal stance, and somebody comes up and pushes me, I'm going to resist that because I don't want to fall over, right? So I'm reacting to the stress. I'm trying to re-equalize myself. Same thing with a teeter-totter. If my reactants and products are equal, and then I put more things on or take something off, then I'm not equal again. So I've got to shift to make it equal again. And that's what the Le Chatelier's principle basically says, is that a system will undergo change so it's back to equilibrium. So this is how I do it, and this is how I remember to do it. When you're on the test, I write down the equation they give me, okay? Because they're going to ask me questions about it. And I take a pencil, and if it's adding, I put an arrow on top. So adding reactants, that would mean adding reactants this way. Now, if I'm adding, I go back to thinking about when I was growing up. My dad used to always get topsoil, it seemed like, every year. And then they would dump the dump truck, and we'd have to spread it around the yard, right? So they added a pile, and we equalized it throughout the room, throughout the yard. Well, we also had a dog that loved to dig. So the dog would dig out holes, and we'd have to go back and fill the holes up. This one is like putting the big topsoil pile in the front. So I'm going to spread it around the room, around the yard, okay? Because I spread it around, it's going to shift to my products. So if I put in pressure on this side where I have a lot of people on one side of the teeter-totter, I've got to equalize it by shifting some more to the other side. So this one's going to shift towards the products. And now I'm going to erase that. And the next one, it says removing. So if I'm removing something, I put an arrow underneath pointing down. So I'm making a hole, right? That's a dog. He's making a hole. Now we got to go fill it. How are we going to go fill it? Well, we've got to shift some stuff over and fill it. Okay? So if I'm shifting stuff over to fill it, it's going to shift to what? Shift towards the reactants. Good. Okay, I'm erasing again. I'm using the same thing. Use green this time. This time I'm adding products. So I'm going to put the arrows coming down here. Which way is it going to shift? Okay, towards the reactants, because I'm going to shift. I've got to cross the arrow. Okay, so I've got to follow the arrow pathway. So it's going to shift towards the reactants. Okay, last one, removing the product. So my dog's dug a hole and I got to go fill it, right? So which way is it going to shift? Show me with your fingers. I want to see everybody's getting it right. Fingers or thumbs, I don't care. Tell me which way it's going. Some of you are going like, wait until my neighbor does something. It should be going that way. So it crosses and goes the same direction as the arrow. You notice that? Okay. So if I'm pointing down, the only way I can cross this is coming and going that way with the arrow. So it's going towards my product. So shifts towards products. All right, so let's go to the next one. We can also do it with pressure and temperature. So not just putting stuff in or taking stuff out, but we can heat it up or we can apply pressure. Pressure only works with gases. So if I have anything that's not a gas in the equation, I ignore it. I only work with gases. And I work with the coefficients of the gases. So over here on this side, I have 4 moles of gas. And on this side, I have 2 moles of gas. Everybody see that? So I would ignore any liquids. I would ignore aqueous. I would ignore solids when it's talking about pressure. Okay? Now, you got to be careful because this is where she's going to trick you a little bit. She's going to say decrease the volume. Well, if I decrease the volume in something, I'm going to increase the pressure. If I expand the volume or open up the volume, what am I doing to pressure? Pressure's going down. Okay, so we're also going to talk about temperature. So let's do temperature first. Temperature is always going to be your kilojoules, or we say heat. And we do the same thing that we would have done with any other adding or subtracting of stuff. So if it says temperature increase, that means I am adding it in. Yes? Okay, so if I'm adding it in, which way is it going to shift? Show me with your fingers. This way, good. So a shift away from it, it has to cross the arrow, right? Following the arrow points. So I'm just going to put this way. I'm getting tired of writing shift towards. You guys get the idea when we do this to the arrows? Shifts towards the reactants or the products. So this would be towards reactants. Okay, so let's look at the other one, temperature decrease. So that means I'm pulling that thing out. That means it's going to what? I'm digging a hole. I got to shift towards the hole, fill the hole. So it's going to be towards my products. Okay? I'll put the R or the P there for you. Okay, so let's erase those 2 lines so they don't get in our way. And let's talk about pressure. So if I increase the pressure or decrease the volume, what's going to happen to the moles of gas? Which side is more favored if I'm increasing pressure? The right side, because there's less, yeah. So if I'm increasing pressure, instead of having 4 people run around, 2 couples are a lot easier in a smaller place to, yeah, anyway, we'll just go that way. Okay, pressure. Okay, so that then the bottom one, if I decrease the pressure or increase the volume, it goes to the side that has the more amount of moles of gas. So I would go towards my reactants. Okay? Questions so far? Are we doing okay?
So what does the mold even do?
The moles just is for pressure or volume. So she won't give you both. She'll say decreased volume. And you've got to know increased pressure. Or she'll say increased volume. And you need to know that means decreased pressure. Okay? All right, so now we're going to be more specific. Here we've got an actual equation, and we're doing specific things. So here I have CO is added. Which way is it going to shift? Show me with your fingers. Yeah, away from it. So if I'm putting it in, it goes away from it. So towards the products. What about H2 is removed? So, oh, here's H2. I'm removing it. Which way is it going to go? Towards the reactants. Good. What about H2O gas is added? Which way? I want to make sure everybody's getting this. So if I'm adding it, go away from it. Good, so it should go to the reactants because I'm going away from it if I'm adding it. If I'm taking it out, I'm going to it. All right, so we're going to come over here. I'm going to erase these arrows because I'm going to use the colors again. Okay, CH4 is removed. All right, that's removed. Go towards the hole, right? So we're going towards the products. And volume is decreased, therefore pressure increased. Okay, well, wait a minute. I've got to look at the moles. So 4 moles on this side versus 2 moles on this side. Which way am I headed? Volume is decreased. Good. It should go towards the products because the products have less number of moles. Okay, then we've got heat is added. Oh, that has to do with kilojoules. So I'm just going to put an arrow going down there. Heat is added. Which way am I going? Away from it, right. Towards the reactants. So you should be able to do these pretty fast. Are we okay? Anybody not getting it? Stop me if I'm bulldozing you. You're not getting it. Okay.
Not really getting the volume and the pressure.
Okay, volume and the pressure. Okay, so if volume is decreased, and that's basically all she will give you. Okay, she won't give you the other. Then I've got to think, okay, if I'm decreasing the volume, then the pressure is going to increase. So if the pressure increases, would it be easier to have 4 things running around in there or 2 things? 2 things. So I'm going to go to the side that has 2 things if the pressure is increased. If the volume increased and the pressure would decrease, then I would go back to the side that had more. Okay, because I have more room. Okay, are we okay? Do we need to go over any others really quick again? Okay, we're understanding it? Great. So we go back to our favorite graph that we've been using a lot, the activation curve. You need to be able to look at an activation curve and be able to tell me what's happening. Where's the catalyst? The catalyst is always going to have a lower activation energy, not a change, a net energy change of reaction. The net change of energy of reaction always stays the same. She will try and trick you there. Okay, so know that when what a catalyst does is just lowers the activation energy. It doesn't change where the product and the reactant are. Doesn't change that. It just lowers the amount of energy it takes to get to there. Okay, yes?
The activation energy from the products.
The activation energy is from the reactants to the top of the curve. For without a catalyst, this is with a catalyst, but it's always from the reactants to the top of the energy curve. The change in energy, now notice I'm saying change in energy instead of delta H because it can be other things besides heat. Okay, the net energy of the reaction is just from the reactants to the products. So it's just that distance, and that distance does not change. Yeah, change in E instead of what we've been doing, change at H. Okay, same thing. It just can be something else besides heat. It could be light, it could be mechanical, it could be whatever. Okay, you need to be able to read off the graph and tell me what's the potential energy of each part. Remember, the potential energy is from the bottom to the top. So the potential energy of the activated complex is from the bottom to the top. Potential energy of the products is to the products from the bottom to the top. So you need to be able to do that. You need to be able to tell me what delta E is, what the activation energy is. What's the activation energy with the catalyst? What would be the difference between with and without a catalyst? Okay, we've done all this. We're okay with this? Okay, if not, come see me and we can go through that again. All right, so these are what she will do with a Le Chatelier. Yes? A catalyst is like a matchmaker. So instead of going up and over a mountain, you found a pathway around the mountain instead. That doesn't take as much energy.
But it speeds it up?
It doesn't necessarily speeds it up, but it does take less energy. So it might take me longer to go around the mountain at a lower energy level than to go up and over the cliffs of a mountain. Okay? All right, so these are the kinds of things that she's going to be doing. She's going to be giving you an equation that has colors with it and asking you what color the solution is going to be if you do something. So don't let that throw you. Do the same thing that we've just been doing and go from there. So the reaction above is cooled. We'll use blue because it's cooled. That means I'm taking heat out. What color am I going to see on the reaction? Which way is it shifting? Shifting this way. So what's on this side? Pink. So this is going to show me pink. Because it is shifting towards the reactants, right? I'm taking away from the product and making more reactants. Okay, let's look at the next one. Cl minus is added. I'm adding this. Which way is it going to shift? It's going to go towards the products, which means what color is it going to be? Blue. See how this works? So it's just one more step from what we've been doing. Okay, and then if we take out CO, and this one threw off the last class, so let's see if you guys do it right. If I take out CO2, where's it shifting? Shifting towards the reactant, so what color is it going to be? It's going to be pink. But wait a minute, didn't we just take out all the cobalt? Wasn't the cobalt the pink if we took it all out? Wouldn't it just go away? Well, what's happening is what was blue now splits back and becomes pink and colorless. And so we're actually making it pink and colorless. Yes?
Will we ever have like pink, where it says pink and colorless, will we have pink?
No, you'll only have one color on each side. One will say colorless. Okay, good question. Are we okay with this? All right. So don't overthink it. I want you to try this one on your own, and then we'll talk about it. Okay, who's got I? What do they think I is? Okay, good. We put in, so we're going to shift towards it. It should be blue. Okay, what about II? Okay, we're removing it. So yes, it should be blue because it shifts to fill the hole. What about III? Brown, good, because we're adding it here. So it's going to shift away and we're going to get brown. So it's not real hard if you don't try and overthink it, okay? So I had a lot of kids trying to overthink it. Let's go on to the next one, see how you did on this one real fast. Same kind of stuff. Okay, let's come back. What about I? It's going to be colorless. Good, because we're shifting to fill the hole, right? So this is the arrow we were looking at here. What about II? Okay, again, we're shifting away from where we're adding right here, so it is going to be colorless. What about III? We're going to be yellow, solid, good. So this isn't that hard as long as you don't overthink it. And for me, the arrows helped. If they don't help for you, then you can just Do whatever helps you. Okay, so what we're going to go on to next is your equilibrium lab, which is your pre-lab. We have got everything done, notes-wise, that you need to take the test. So like I said, if you need to take it this weekend, then work on getting your pre-lab done, then work on doing the pre-test, and work on your sapling. You have got a half hour that you can do stuff in. Make sure you get the pre-lab stamped. If you want to get your graphs ready to go so they're ready to roll when you come next time, you're welcome to do that. Whatever you think you need to get done, okay? You do have to read the procedures in order to set up, do the pre-lab, so that make sure you read and understand what you're going to be doing, okay? Where, if I forgot, there was a couple of kids that said that there was straws in there somewhere. That would be referring to beakers. We tried straws one year and they just didn't work, so we went back to beakers. Okay, so, but I don't know that I went through and fixed all those because I was like, where did you get straws? And I couldn't find it. So anytime you see straw, replace it with beaker. Okay? Yes?
What was that program that you want us to use?
Logger Pro. Logger Pro actually works the best, and you can bring it up and sort of look and see what you would need to do to work with it. But like I said, if you're more familiar with Excel, you can do it in Excel. Okay? All right, time is yours.